All right, this is our last little lecture for Lewis structures, and it's exceptions to the octet rule. So normally we go for an octet, we want to have a full 8 electrons on every single atom in a Lewis structure, but there are some times when that is not going to be the case. Before you watch this lecture, make sure you watch the one on formal charge, because some of this will not make sense unless you watch that lecture first. Repeat, watch the lecture on formal charge before continuing on with this one. Okay, our lesson objectives. We will make Lewis structures for compounds with more than an octet, and we'll discuss why they have more than an octet. We will make Lewis structures for compounds with an odd number of electrons and discuss where those electrons go and why. So exceptions to the octet rule can include the case where you have more than an octet. So if your atomic number is greater than 12, then you can open up the D block to bonding, which obviously the D block has 10 possible positions, so 10 plus 8 is 18. So when does this happen? When you have a cation that is paired with highly electronegative elements such as fluorine, oxygen, or chlorine. When the expanded shell results in a smaller formal charge on the atoms in the molecule. And finally, if you're adding double bonds to reduce formal charge, it only applies if you must violate the octet rule to represent the molecule with single bonds. So you have to have greater than 4 outer atoms in order to violate the octet rule with a double bond. Otherwise, don't do it. Just don't do it. No matter what the formal charge is, just leave it alone. Okay, moving on. Let's try this thing. All right, SF6. This is an actual compound that really exists. So if we follow our rules for making Lewis structures, we put the sulfur in the middle, we put fluorines all the way around the outside. We have 6 plus 7 times 6, 48 valence electrons. All right, so we put in our single bonds, we fill our octets, and we have a structure here which has 48 electrons. Now, if we go and we do the formal charge for our sulfur, you have 6 valence electrons minus 6 bonds. That is a formal charge of 0, which is what we like. If we take the formal charge of each fluorine, they're all the equivalent. We have 7 valence electrons minus 6 unshared electrons minus 1 bond gives us 0. The formal charge on everything in SF6 is 0. Fluorine is highly electronegative. Sulfur has a Z greater than 12. And we do, in fact, have more than an octet. So this is one of our exceptions. Okay, so we can see that this worked out. This was okay. There are actually plenty of examples, and there are a bunch of examples that you're going to see either in lab or in other places where your molecule includes a noble gas, which is somewhat surprising, but you have to remember our effective nuclear charge is going to be lower and lower the further you get away from the nucleus. So if we are talking about the noble gases that are on the bottom of the periodic table, some of those electrons can be coaxed into bonding. All right, now we can also have a situation where we end up with an odd number of electrons. In this case, it is impossible to make a full octet, so the octet rule cannot apply. We'll do an example with nitrogen oxide, which has 11 electrons. And there are 2 options that I can readily think of. So we have nitrogen single bonded to oxygen, and we put 3 electrons on nitrogen, and we have 6 electrons on oxygen that are unshared. Or we could have nitrogen double bound to oxygen, and we'll have 4 unpaired electrons on oxygen and 3 on nitrogen. I put the 4 on the oxygen because the oxygen is more electronegative. So which one of these is more favorable? We will go to the formal charge. We want to have the lowest possible formal charge. This is why we needed to do this before we got to this lecture. Okay, so if we do nitrogen, we have 5 valence electrons minus 3 unshared electrons minus 1 bonded electron. That gives us plus 1 for nitrogen in nitrogen single bonded to oxygen. And then if we do the same thing for the oxygen, we get a negative 1. Now, if we go to our second example where we have a double bond, we have 5 minus 3 minus 2, which is 0, and the oxygen is also 0, 6 minus 4 minus 2. So our favored configuration is going to be nitrogen double bonded to oxygen. The oxygen has an octet, but the nitrogen does not, because we cannot have an octet when we have an odd number of electrons. You will see this most often for nitrogen-containing compounds. One of the reasons that our nitrate and our nitrite polyatomic ions are stable is because we actually have that nice extra electron, and we don't have to worry about this lack of an octet. And just as a reminder, the reason why we normally want to have an octet is because that's a full s and a p orbital. 2 plus 6 equals 8. All right, let's summarize this. To summarize, for atoms with an atomic number greater than 12, which makes the D block accessible, you can have more than an octet. This will happen when paired with highly electronegative elements such as fluorine, oxygen, or chlorine, when an expanded shell results in a smaller formal charge on the atoms in the molecule, and finally, reducing formal charge as far as the structure, like adding double bonds, only applies if you must violate the octet rule to represent the molecule with single bonds. So in other words, if you have more than 4 outer atoms to begin with, you can start making double bonds. For atoms with odd number of valence electrons in the compound, you will have less than an octet, and again, go with the lowest formal charge version available.